Alright, let's try to solve one of the problems in your last homework, okay? It was this simply supported beam A, B, C given, right? Oops, A, B, C given to you guys with a distributed load on top, right? That whose maximum was given to be W naught. This W naught is then the density, like the load density on top of the beam, which could have been a number. Now it's just a parameter. Let's deal with it. What it's asking for this problem is, hey, plot basically the shear diagram and the shear and moment shear, and then the moment diagram. Okay, as a function of x, both of them are varying along that direction with x direction. Okay. Before even getting there, what we should do is doing the first step, the free body diagram. We gotta figure out what forces are applied to this beam of ours. We know these supports. Those supports do not have any moment reactions, but all they have is the vertical reaction forces that, like, let's call them RC, and then for this other guy, RA. Okay, how do we find them? We basically, now, give me one sec. Alright, that's better. How do we find it? Basically by doing our equilibrium equation. Equilibrium equation. One of them was like by writing the force balance and then the moment balance, like force balance in vertical direction should be 0, and then sigma m should be 0. You all know that from your statics, right? That's what we normally do to find RA and RC magnitude. But here, one observation that we immediately make after we see this problem is that, hey, this loading is totally symmetric. What does that mean? It means that each of these supports are essentially supporting half of the total load from the top side, which is being applied to it. So that means my RA is the reaction. RA should be equal to reaction RC, equal to half of the total loading on top. What is the total loading on top? You can show it with F total. This is going on in my scratch paper, right? F total should be the area, the total area underneath this guy, the area of that triangle. It will be base, which is L, multiplied by height divided by 2. That's the total force. Now half of this is going to get there, which is LW naught over 4. Okay, don't need that part. Alright, now we have it without even having to go through the equilibrium equation and all that. Okay, let me just make enough space here. LW naught over 4. Okay, put that in triangle. We got that. Sometimes in some questions like you are actually given the amount of that, so you don't have to find it, but here we do need that. All right, after this, the next step is, how do we plot it? Let's make the environment of the graphing ready. We go underneath it. The first thing we do is graphing y versus x. Well, there are several ways of plotting shear and moment diagrams. One of them is totally analytical. You find a formula and then plot them. The other one is the area method, which is easier. Even to do so, different people have different approaches. Some just do it graphically, some integration, some the combination of both. Okay. Well, what I usually use, especially when I find it more comfortable or convenient, less likely to make mistakes, is doing the integration method. And even the problem gets complicated, I find it easier to do so. So the only problem that you can make is doing your integration wrong. But that is also, you can also check that, you know, by like, that's why I'm saying the combination of graphically and integration. So let's see how it works. What we all do is starting from the left side and gradually building up, and the like essentially starting from the point force at the very left side, and then calculate how much load we are accumulating as we go to the right side. Okay, that's going to be our approach. At here at x equal to 0, what we have is this RA, is that amount of force. All right, I'm going to apply that on the graph. All right, so RA, let's say it would be here with amount of LW naught 4. Yes, something that you may get confused at this point. Look, remember how we were talking about those convention, right? The convention, what convention? I was talking about this is downward is negative, is positive. Clockwise is positive. Clockwise is positive, and then this smiley face in our moment was positive. This is not where you are. You have to consider it. Like maybe it's a question. It's like, why does she put that positive while this is upward and it has to be negative? Nope, this is not the case that you're using that convention at this point. So if it's upward, right? Like at this point, you go LW naught over R or whatever the magnitude is up. Okay, because it's telling us to go up, essentially. All right. Okay. Then now we have to take care of this distributed force over there. Remember, this you gotta remember for that I wrote on the board the other day. I wrote Wx is equal to minus dv, or derivative of shear, versus x, okay, over x. Well, I prefer here to show the loading with L instead of W, okay, just so that you won't, it would be easier to see and not confuse it with W naught, which is only the maximum amount for it. Okay, what this tells us is essentially that I can, it is dv equal to minus L x dx, and I can integrate from the both sides and end up eventually being able to say that Vx is minus integral of Lx dx. That's what I pinpoint as important, and get rid of all these. That's what you want to remember. What you want to remember is that, or essentially what this means is that if I have that function, if I have that curvature Lx plotted versus x, all right, if I integrate that, or if I find the area underneath that curvature, that is essentially going to give me the v. V was a shear, right? And then I can plot it right there. Be very careful about noticing that minus. Don't drop that when you're doing your integration. Okay, that being said, so first step is what we first see is that loading, that line. So we are about to write the function of that loading right here. That is a linear function. All of us remember that such a curve or such a line has this general form. That's a linear function. That being the slope, and being the slope, and then b being the intersect. Following that, we will write the equation. The slope of this curve, I keep writing on top of it. The slope of that guy, oops, is going to be basically delta y over delta x, positive. It's going upward. Essentially, the slope is positive. So it would be W naught over L over 2x plus plus basically the intersect, which is 0. Alright, I don't even need to show that. Okay, so that is what we are going to put right there, and then integrate it, not dropping the negative, and then find the RVX. So that's what I'm doing right now. You can keep that on your paper, you can do all this on your scratch paper, I don't care. Let's find it. Vx, sorry. Alright, Vx therefore is going to be minus integral of w naught and the 2 there x dx. Okay, which I write it quickly here, that x dx, you gotta remember the integral of that is 1 over 2 x2 plus some constant. Okay, we don't want to, you can actually differentiate this side and you have to get x out of it. Okay, let's use that principle of integration right for here, for our case. That would give us minus 2w naught over L, which is a constant, so it comes out of the integration. X2, we don't forget about the 2. X2 plus a constant. We tend to show the constant with C naught in this video at least. Alright, that is RVX. What I'm missing here is C naught. I gotta find that number, what that constant is, with probably the boundary condition, or if I know x, or at if I know v at some x, then the only unknown is C naught, so then I can find my C naught. Well, looking back here, I know that at x equal to 0, the shear is LW naught over 4, so I applied to that equation in order to find C naught. That being said, it will essentially be that those two would go away, minus W naught L. Where was I? Oh, that was, I'm putting 0 here, so 0, that would be 0, so plus C naught, so my C naught is essentially that number. So I plug it back right there and write my equation nice and neat up here. I don't need that anymore. Okay. So Vx for the left hand side, the left part of the distributed force is going to be is minus, make it smaller so I will have room to write. It will be Vx equal to minus W naught over L x2 plus the C naught that I just found, which is LW naught 4. Okay, box it up. So I'm going to plot that right in a second and get rid of everything else I scratched here. Alright, so I'll give you a quick recovery sort of from your math classes, is that if you look at such function, which is essentially a quadratic function of degree 2, right? That if this number is a positive number, you remember, it would look like something like that. That if that intersect has an amount of a, this curve would be something like maybe y2 plus a. If I were to plot y minus x2 plus a positive number, what I would do, or what it would remind me of very quickly, that it has this kind of general form. It would be sad. It would the curvature is in like sad mode, unlike this positive mode that this was that. So minus is showing me this kind of curvature, plus a, it means that it should be shifted. So sorry, if this is alright, this, oops, this is actually y something minus x2. If I add plus a to it and a is positive, then I shifted a much upward, and that would be my graph. Anyway, that's just a general. It will help you with your plotting if you know these things. I'll show you why. You don't need to find the exact. You don't need to like exactly plot the curve, right? You just have to do an approximation of it, unless you have a particular reason to do exact. Okay. Anyway, so in order for me to find it, to plot this curve, I essentially need 2 points. One of them is already known at x equal to 0 here. My v was that. So I start from there. The other point I would like to find, you can, is like, hey, I ask myself, where is the point? At what x essentially my v becomes 0? v0 at what x? Well, it would be, I'm going to put that equal to 0 and find x out of it. Yeah, which is known as w1 l x2 plus lw naught over 4 should be 0. Okay, so this is how it is going to look like right down here. Right, I'm saying minus w naught l at some x2 is equal to minus l w naught over 4. That is gonna go away. That is gone. So what I'm essentially end up saying is that x2 is L2 over 4, therefore x is L over 2, or at least only the positive L2 is acceptable. So I plan, what I am going to pinpoint in my curve is that x equal to L over 2, which is right below here, my v0, so the curve is going to pass from it. So now that knowledge of knowing happy or sad thing is going to help us here, because this is negative. The curve that I'm putting right here should be part of this curve, not the top one. Like, for example, if you don't know that, then you're like, oh, I gotta connect these 2 points together, but like, is it going that way or going that way? This one bottom is part of the positive side, right? This is like this, and this one is referring to this portion of the graph. That is why we choose. We are like, nope, that's a bad idea. Actually, my curve is the acceptable one is that. All right. I gotta clean this, and yeah. So this is this is what I got. Okay. Now now I'm going. Now I like to plot this other side of the graph. Okay. I do the same thing as I did to find my Vx for this other part, and then plot it. In order to do so, okay. All right. That was L. Oops. That was L that I missed. Alright, let's not you lose that. The others are, now I am focusing on this right section and going to find L function for that part. One part that you are going to pay attention to right now is that in order to find this function, I am going to shift the coordinate system from what it was previously, which was here, right? For the previous one, I plotted Vx with x, or essentially, sorry, I found Lx versus x with that in that coordinate system. Now I'm shifting my coordinate system to the right, starting at point B, and I'm going to find my loading function. All right, you will see why. It's just way more comfortable. You don't have to do that. It's just it's just easier. It just makes your life easier when you want to plot it. All right, let's do this. All right, L. So right now we're focusing on this other side, the green side. That is what I am writing the function of. Again, it would be a negative slope. It's a negative slope. The slope is still delta y over delta x, but negative 1 minus w over L over 2 x plus d intersect. It starts at w naught. Agree? Okay. Now, making this. Alright, that's essentially, I bring the 2 up. Now I put this function back into this, here integrated in order to find my Vx. Okay, so it turns out Vx, and not missing the negative, it will be 2w, well, don't forget it has 2 negatives, so negative, negative, positive 2w naught over L x dx, and the next one, that's a plus, so it becomes minus integral w naught dx, or you don't really have to show 2 of the integration. You just can say, you can just like, oops, I'm integrating that guy, which is essentially integral of that and that one added to each other. This becomes 2w naught L, you remember, x2 over 2 minus w naught x plus a constant that I show with c naught. Alright, so far we got here. All I need to find is now finding c naught. C naught, put it back here, and then write my function clean and neat up there. All I need is a point that x and y of it, x and v of it are known. Well, I have that. At x equal to, remember, at x equal to not L over 2, but x equal to 0, because I shifted my coordinate system. Start 0 at there. At x equal to 0, v is actually 0. So I apply that to this equation and find c naught. X equal to 0, that would be gone, that would be 0, that would be 0, v would be 0, so my c naught is essentially going to be 0. Okay, I'm just substituting x and v in this function, which, or like it was this, I mean, that's how you write. And you find c naught, and, oops, here, I write it, I don't need that anymore. I bring the function here and write it. So Vx for the second part would be, it's W naught over L x, oops, twice. So this app is not easy, especially it's my first time working with it. W naught L x2 minus W naught x, and C naught was 0, so we took care of it. Okay, cool. Alright, I delete the rest because I don't need. Alright, one sec. Alright, I box this because I'm going to use it again soon. Alright, now all I have to do is plot this guy back in here. Okay. How do we find it? Well, it starts from this point at x equal to 0. Don't forget that. That was our new 0 for this. Now, so for this would be our, this is basically x equal to L over 2 in our new system that we're talking about. So if I plug this in here in x, then it will give me the intercept at which the graph is actually, I don't know, is it here, wherever that is. So I find that, therefore, here is how I like to show is my v equal to L over 2 is equal to, like some people, like, you can even put a prime so you show that like you're using a new system, but really at the end of the day everyone is like looking at your graph. So okay, so that is so you're plugging in that, so it would be W naught L over 2 minus W naught L over 2, okay, which is equal to W naught L2, which then it will be gone with this other L, so I just don't write it, right? L over 4 minus W naught L over 2. Sweet. So basically, this guy minus, or the subtract of both of them, this results in minus, it's minus 1 or minus W naught L over 4. Okay? Which here, oops, again, back to white, chalk, so it would be here perhaps, and with the magnitude of minus, or with the magnitude of L, W naught 4 down here. Then I have to connect these two together. I have two options going that way or that way, like easily, well, right, I don't know how to connect them. You can go find another point right there by applying, I don't know, some x between this point and that point to the function, find it, or come back, look at this, see, oh, W naught is positive, L is positive, so this whole number is going to positive, so AX2 is positive, it's a smiley, it should be part of that smiley graph, so you will accept that one. What, or any way that you like to plot, we don't care. Okay. Oops. That. Anyway, that would be your final results. Well, we're not done yet. Well, we just got at the end to point C. We're just done with our distributive force, right? But as we started with a pin, we went through the distributive force, and now we're at point C, and we have to gotta take care of our C, which means we have to go our C much up. It's showing an upward direction to us. Therefore, I continue our C much, which turns out to, oops, cancel out. Oh, I know what's happening. Okay, I will end up here at 0. If you do not end up at 0, then you did something wrong. Okay, now that we have our sweet little graph of shear, let's move on and plot the moment. Okay. Maybe. Alright. I'm going to take the scratch paper to the next page. Alright. Or maybe I can do it here. I don't know. Hopefully we'll have much room here. Let's do it. So another thing to remember. Okay. Yeah. Alright. So now, let's clean that. So I'm preparing. Oops. I'm preparing to plot down here. Well, not very successful. Alright, x. And this is going to be my mx. Okay, that is all we need. Alright, what you gotta remember here is another formula like that I put on the board, and that was what? That essentially your moment, that essentially your moment is equal to integral of basically let me write what. Okay, oops, come on, white, back to white. All right, so what we had is that dm over dx, this is the original formula for it, and that's it. V is differentiation of moment. Okay, it's basically what it says is V is the slope of this curvature, the slope of M curve at every single point of X. Alright, what that also means that we're going to use to plot is, again, I'm doing the similar thing as before, integrating, so that would take me to the fact that mx is integral of this shear force, which means the area underneath this graph is going to give me the moment. Or simply, if you find this curve, if you have this function, you put it here, integrate it, and find the moment that you are going to plot back here. Alright, what all, I guess I will leave that for you guys to see here. Okay. Let's go back to white. So the other formula that we are going to use is right. Alright, that's clean, sorry. Okay. With, I don't know, with red, I guess. Or like that, fine. Other formula would be mx equal to integral v x dx. Hopefully that's clear. What do you need on your cheat sheet? You want to have that, you may want to have that, or the original form if you're comfortable with working with it. Okie doke. That all said, so this is our first function, this is the second one. We plug both of these guys into that and integrate it, find our moments, curves. Let's do it. My hesitation is, again, I have a problem with there's no space here. Alright, M, I'm going to write it real. So for the first one, mx, I'm plugging in this first, the red equation, which is minus w naught L over L x2 plus LW naught for and integrated. Well, maybe you want a reminder? The reminder is the fact that integral, well, we said x dx, the integral of that is 1 over 2 x2, right? So what is the integral of that guy? Which is like x2 tx, x 1 over third x3, okay? Good if you remember. That said, white, okay. That said, this guy's turns to be minus w naught L x3, don't forget the 3 down here, plus this one is a constant number. Every time I'm doing, I go back here and check, oh, was there as a sign? Like, to make sure I'm not doing any mistake. In my integration, 4, that's turns to be that, right? A constant number whose integration become the first order with x, okay, and then x3. Alright, don't forget the constant plus which is C0. Okay, once again we gotta find C0 here, so we will have a nice clean function of m. What do I know? I know that there is actually no external moment happening in my system at any point. So when I start again from left to right, at 0, there is no moment. Okay, so basically what I'm saying is that m0 is 0. Right? So substitute x equal to 0 here, and then find c naught. C naught turns to be 0. Okay, so that would be 0. Let's write that equation clean and nice here underneath everything else. So mx for the first part, like that, is equal to minus w naught 3 over L x2 plus lw naught over 4 x 0 plus 0, which is nothing. All right. That now I have to plot underneath here. Okay. Well, what I can did I not put what I missed here? Something I missed. Oops. Let's go back. That was x3, right? I missed an x3 here and then x here. I don't know why. Let me correct that on the board. Wait. So what I'm saying is that this dude was x3 and then I missed an x there. Okay, now it's correct. You can go back in the video and see why. Alright, W naught, yep. Alright, let me make sure I got it because I cleaned it on the board, so make sure I have it correctly for you. X turns out to be, alright, minus Vm minus W naught L3 x3 W naught L. Did I? Alright, that was 4, right? I don't know why I made that mistake. Writing W naught. Yeah, you got it because we got it from that one. So in my head right now, I'm integrating this one again to that. That's totally correct. Sweet. Alright, now that we have this equation, we gotta plot it. Alright, here you can remember x3 functions, just like essentially like that. You don't even need to know that it's just like a curvature. What you do need is, like, again, 2 points on your moment graph. Let's say at point 0, I already told you at point 0 it's 0, so it starts from that point, this point, and then it goes. Let's see what happens when it reaches to L over 2. Okay. Therefore, what happens at L over 2? Note that our coordinate system right now, or the integrated within that coordinate system I just showed, putting that back in here gives us m being what? So I'm going to scratch paper 3L. That would be L over 2, then 3 plus LW naught for L over 2. I find that one and it turns to be minus W naught. Well, I'm just writing it so you see L3, 2 to 4, and then this one becomes 8. So 8 then multiplied by 3 will get us 24. Do I have anything? Nope, done. L3, then plus, on the other side, I have, oh, the L3, and then L would be gone, so I guess I can imply it. Imply it right here. Okay. This turns to be L2. Okay. LW naught. Where am I? L2. That would also give me L over 8 L2. So you will just add these two terms together